Hey everybody, welcome back to the episode number 5 in this Fundamentals of Sequencing video. So in this object, we're talking about the ramp object. Last time we talked about what, and what does is turn ramps into impulses. Ramp does the opposite. It turns impulses into ramps, which can be really useful, particularly for generating envelopes and also for playing back samples. So let's get into it. So we're going to start here on this Basics tab with a really simple example. So what we have here is in the upper left-hand corner is a phasor at 0.5 hertz or 120 beats per minute, going into a subdiv object with a prob attribute set just to get some kind of random events. And then using this pdm.rampDetect abstraction, which is from that what video, and I'll put the link up here, wherever that is, to create some impulses. So returning a bunch of ramps that the subdiv object produces into a bunch of impulses. And then we are turning those back into ramps. Now, why exactly do we do that? And the reason is because ramp allows us to control the length of the ramp, basically the amount of time that it takes to get from 0 to 1 in milliseconds. So where a subdiv produces a bunch of ramps, it's always producing them as some subdivision of the phasor that's coming into it, right? So if we create some scopes here, this main phasor is kind of representing a bar at 120 beats per minute. And the subdivs represent a 16th note, so some subdivision of that. But when we're doing things like determining not so much when events occur, kind of what the timing meter of our patch is, but rather want to indicate the amount of time that an event takes, like describing the amplitude envelope, very often we want to use sort of an absolute understanding of time, so something in milliseconds. So that's what we're doing here. If I set this to 250, those ramps are going to be 250 milliseconds long, at least when they make this full journey from 0 all the way to 1. You can see that not all of them do. And those are the cases where a ramp came in before an impulse came in before the ramp completed. And it restarts the ramp because I have this retrigger 1 attribute set. If I disable that, it's actually just going to ignore any impulses that come during an uncompleted ramp. So you can see we're actually getting fewer ramps there, but they're all complete. Whereas if we enable that, we're always going to get ramps. And you can see down here that it's very easy for us to convert those ramps into gates. So we can think about this as a really easy way to get into the kind of stuff that, say, modular synthesizer would expect, right? And you could send this to if you have an audio interface that is able to send CV, then you can send a gate to your synth, just like this, by checking to see, hey, is the value that ramp is producing greater than 0. One thing that's kind of a cool feature that's built into this actually is that when the ramp completes, it goes back down to 0, right? So it makes it very easy with one object for us to derive a gate. And if we want to change this value, actually, say we did 0.5, then we can set the length of those gates relative to the length of the ramp. So because the ramp object allows us to take impulses and get out ramps in milliseconds, we can think of it as kind of being like a signal-driven version of the line tilde object. So line tilde produces a signal, but it does not receive signals. So if I give it a value of 0, and actually I'm going to grab a scope here, and I pass the message 0, and then I pass 2000 milliseconds to the right inlet, and then I send 0, it's going to produce a ramp over 2 seconds from 0 to 1, and it actually stays up at 1. And this is all well and great, but if I want a signal ramp, very often I want to, almost always in my case at least, I want to initiate that ramp with a signal, and that's what the ramp object allows us to do. One other feature that it has, which makes it all the more similar to line, is give you the ability to determine what the start and end points of that ramp are. So if I turn things back on around here, I have this R slider that's set up to be on the range of 0 on the left to 1 on the right. And if I draw some smaller region there, it'll produce a ramp of that length, 250 milliseconds, over that shorter distance. And I could go beyond the range of 0 to 1 if I wanted to as well. So that is the basics. Let's now get into one simple application of this object. So here we're using the object with another of its cousins that came out with Max 8.3. This is called shape tilde, which is meant to be used pretty much always with function, which is over here on the right-hand side. And when you create a function in its default state, let's actually do that. I'm going to copy this and I'm going to paste replace. You just get this blank square. And I'll draw some points in here. I'm going to draw 3. And what the shape object will do is take this shape, this function that I've drawn, and anytime that I draw in this window, anytime I move these points around, when I finish doing that, the object from its right outlet, the function object from its rightmost outlet produces a bang. And I'm actually routing that bang back around into the first inlet so that from the second outlet, it sends this list into the shape object. And that list describes, shape understands what this list means. It describes this shape. Shape tilde is then capable of playing back that shape in response to a ramp signal. So if I move this around, you can see that I'm now producing that shape. And if I add some points, you can see that I'm getting those as well. For me, most of the time when I do this, I really just want the 3 points. So the beginning, the middle, and the end. So this is kind of like an attack release envelope. But if you wanted to do something wilder, you obviously could. And the speed at which this gets played back, like if you've ever used function with line, which is kind of what it was designed to be used with in the first place, function has this thing called the domain, which is basically the kind of number of milliseconds that the x-axis represents. That doesn't matter when we use this with shape. So when we use it with line, basically the amount of time that it takes to get from here to here is 1,000 milliseconds. But with shape, actually, those are arbitrary. And the length of time that it takes to kind of go through that envelope is basically the amount of time that it takes to go from 0 to 1 with our ramp. Because the ramp kind of it's almost like we're reading back by scanning horizontally through this function. So if I increase this value, you can see that we play back more slowly. And actually, we're getting kind of truncated here. But if I go shorter, let's say like, I don't know, 50, you can see we go through this super duper fast. So it's kind of cool because it allows you to generate envelopes whose length is actually relative to the ramp, right? It allows us to basically draw a shape and then play back that shape at, however fast we want to. While we're here, I want to talk about a few parameters of this function object that I think are really useful. So one is this mode attribute. So by default, the object is set to linear mode, but if you set it to curve, this gives you this really cool capability, which is if you hold Option or Alt on Windows and then click and drag over some line, it allows you to change the shape of that line. And if you saw the bouncing ball rhythms video that I made, we talk more about this. I'll put the link up above. And that allows you to kind of change the shape. Let's actually go back to, I don't know, something like 200 here. Change the shape of that envelope. Another thing that I find useful is click add. So click add basically says whether or not you can add points by clicking. If you disable that, then clicking doesn't add new points, which once you know how many points you want in your envelope, it's often very useful to disable that. Another thing that I find useful is the ability to basically make it so that my points, particularly the the bottom two are always at 0 because I don't want to be in a situation where I have something like this, right? Because if I'm using this as an amplitude envelope, like if I have some sound and I'm scaling that sound by this function, then the sound is only going to be quiet if the value is 0. So what I'll often do is set this grid step, which is kind of the resolution of the y-axis, to 1, and then enable snap to grid, which means that the only eligible points are 0 and 1. So you can see if I try to move this middle point and I try to move it down, it doesn't move down until I kind of get below halfway. And that just sort of prevents me from accidentally creating an envelope that doesn't sound good because it doesn't actually shut up. You can then change kind of the total amplitude, the total loudness of the envelope by just scaling the result by some number between 0 and 1, or even more than 1 if you want to get crazy. So that's a really simple envelope example, kind of like hyper useful, and gives you a cool little UI object, which is awesome. All right, so let's look at another envelope example. So this is going to be the last one was sort of an AR envelope. This next one is going to be an AHR. And again, we're kind of using ramp to drive it. And actually, let me set some things up here. Let me initialize a little bit here. So here we have 3 params up here at the top: attack, hold, and release. And let me actually play a sound for you, so you can kind of hear what that sounds like. And actually, I'm going to simplify the sequence here. A little more boring, but a little bit more easy to understand. So the envelope that we have here now has these 3 parameters. One is the attack, so the time for it to get to its full amplitude. The next one is how long it should stay at that amplitude. And then the next one is, once that's all done, how long should it take to get back down to 0? And the way that we create this is we start with a ramp whose length is equal to the sum of the attack and the hold parameters. Okay. And then, just like we did in the basics example, we actually convert that into a gate. So that rather than a ramp, it's just going up to 0 and then, or going from 0 up to 1 and then back down to 0. And the amount of time the length of that gate, sort of the horizontal distance of that gate, is, in this case, 41 milliseconds, right? The amount of time, the attack plus the hold. Then we use this rampsmooth object, which does a linear interpolation. So basically, when the signal goes from 0 to 1, the rampsmooth object is not going to make that transition immediately. It's going to basically smooth that transition out over some amount of time. And the arguments here that we have establish the amount of time that it takes for those transitions to occur in samples. So if I go from 0 and then immediately to 1, in the default state of this, the way this object is set up here with these arguments, it will make that transition from 0 to 1 over 5 samples. Here I'm setting the values in milliseconds. So what I'm actually doing is passing that attack value, in addition to adding it to the hold value to kind of generate the ramp of this particular length that we need. I'm also passing that attack value into this very simple subpatcher that's just converting it from milliseconds into samples. So if I make this something longer, like 100, we're now telling the rampsmooth object, anytime you see a change in signals, smooth that change out over 4,410 samples. And you can see that the result that we get right here is a straight line, where prior we had just, or a diagonal line rather, where prior we had a vertical one. So the rampsmooth object basically will smooth out that change from 0 to 1 that the gate produces and create the attack phase of our envelope. Once it's there, then the gate is already high, so it just stays high until we get to 140, right? So the first 100 is the attack, then the 40 is the hold. So for the next 40 seconds until we get to 140 milliseconds, nothing happens. We just stay at 1. And then the gate falls back down to 0 And then the ramp smooth object begins the release phase, where it ramps from 1 back down to 0 over, in this case, 150 milliseconds. And we're doing the exact same thing here, where we take millisecond value, convert it into samples, and pass it into this the third inlet, the rightmost inlet of the ramp smooth object. And that tells the object how long of a time to ramp from in this case 1 to 0. So that's a basic linear AHR envelope. Down here, we're adding a little bit of extra capability, which is actually the same kind of linear to logarithmic shaping that we have over here. So if I come back over here and I increase this attack value, let's say, you can see that it's becoming more down here. You can see that it's becoming more exponential. And if I decrease that value, it's becoming more logarithmic. And then the same for the release. And I have independent control over these things. So I can get this kind of shark fin thing, which is kind of cool. See how much I can really make it look like a shark fin. Here we go. And yeah, I have independent control over each of those. So here's how we do that. Basically, what we want to do is get separately the attack phase, the hold phase, and the release phase, and then apply this kind of logarithmic or exponential like morphing to each of those. So the way that we get the attack, release, and hold is by basically looking at the slope of the line and testing to see, is the slope of the line increasing, in which case we're looking at the attack. Is it the same? Is it not? Is it decreasing, which is the release, or is it neither increasing or decreasing, which is the hold? So change object does exactly that. When we send a signal in, which in this case is like this one, our envelope. And actually, let me add a release phase so that we can see. When the signal is increasing, the change object outputs 1. If it's decreasing, it outputs -1. And if it's the same, it outputs 0. So if we add 2 to that, then we get, if the value is decreasing, we get 1. If it's the same, we get 2. If it's increasing, we get 3. And then we can have, in this selector object, 3 inlets, 1 for the release phase when decreasing, 1 for the attack phase when increasing, and then in the middle, 1 for the hold. And then we have twist objects, which are the things that actually apply this logarithmic exponential morphing. And in the bouncing ball video, again, actually, we talked about this object. It allows us to basically pass a ramp through and do that kind of morphing by using this curve attribute. So here we have the value. So this is where the envelope comes in. And then this is where we get, I believe, the attack curve. And then this is the release curve. Cool. So pretty capable little envelope generator. We'll hear it one more time. Great. So now moving into one kind of more big example, which is using this same object not to generate amplitude envelopes, but actually to play back samples. So I'm going to start here by actually just playing something for you and kind of showing you how it works, and then we'll talk about how to build it. So we have our same phasor subdiv impulse. We have a multi-slider here. And actually, this is going really slow because we're at a div of 1. Let's go to 16. Okay, here we go. Fast. So we have a multi-slider that's setting the pitch of a sample that we're playing back. And that sample is here in this buffer called sound. And we're using the wave object to play back that sample. And what wave does, we'll talk about it in a little bit, but basically takes a ramp and it uses it to sort of say where the kind of read head should be in the sample file. So you can imagine like taking this sample, which is actually, we have it visualized down here. We also can double click this buffer object and see it. And imagine like holding that, on a strip of tape out in front of us, and then moving a little thing that reads back the tape. So like a tape machine works, except rather than moving the tape, we actually move the thing that reads the tape. And so the ramp signal that goes between 0 and 1 tells the wave object where to put that read head, that read device. So what we can do is basically by changing the speed at which that ramp moves, we can change the pitch of the sound that we're playing back by changing the speed at which we play it back. So what we have up here is a multi-slider that produces integers between -12 and 12. And this is expected to be in semitones. So we have plus and minus 1 octave of range. And what we're then going to do is basically use this information to change the length of ramps that are produced by the ramp object that tells wave to play this back at different speeds and therefore achieve different pitches. And one thing that we know kind of from music or from physics, I suppose, is that if we half the speed of something, like if we have a sine wave at 440 hertz, and then we double the frequency of that sine wave. So if we play that wave, let's visualize it. So cycle 440. And let's just plug this straight into the deck. So you can hear that nice sine wave. If we then double that to 880, that's an octave higher. If we reduce it down to 220, then that's an octave below 440. So doubling the speed of something increases it by a single octave. So what that means is when the slider is all the way up at the top here, so 12 semitones up, so 1 octave up, what we want to do basically is play back this sound twice as fast, which means that we want to send a ramp into it that is half as long as if we were playing the sound back at its normal speed, right? If we play it back at its normal speed, what we're going to do is send a ramp in whose length is exactly the same as the length of the buffer. And the way that we can get the length of the buffer over here is by using this info object. So we have a buffer that's called sound. It's got a file in it. The info object uses that same name, sound, which is just the name of the buffer. And then anytime we send a bang, we actually get the length of the buffer. So let's actually, I should have probably already switched over. Let's actually build this thing. So if I take the length of this buffer, and I'm just going to do it like this, actually. So I get the length of the buffer, which is this, 1,286 milliseconds. And I just start triggering the ramps. And let's get a scope for that. And it seems like it's actually not playing the whole thing. So let me fix that really quickly. 0. And 1. There we go. So now it's starting from 0, which you can see. So when we trigger this and we make its ramp time 1,286 milliseconds, then we play the sample back at the correct normal speed. If I double this ramp time, what we're going to do is end up with a signal that is twice the value, which means that we're going to end up with a ramp that is twice as slow or half as fast, however you want to put it, which means that we get a sound that is lower in pitch because we're playing the sample back more slowly. And in fact, the pitch is 1 octave down. If I give 1/2 here so that I play the ramp twice as quickly, now we're playing the sound 1 octave above. So what that means is when the value here is 12, we want a value, we want to get a value of 0.5 times our length, the buffer length. And if we have a value of -1 or -12, then we want to get a value of 2 times the buffer length to generate a ramp that will play this wave back at the correct speed. So let's do that. So I'm already actually storing the list values from the multi-slider in a stash. And if you don't know about stash, watch the video, put it up above. And then what we're going to do is we're going to divide that by 12 so that we're converting this pitch offset in semitones into a pitch offset in octaves. And then we're going to do a really tricky thing, which is we're going to raise 2 to the power of this number. So we're getting a value between -1 and 1, and we're going to raise 2 to the power of that number, which has this incredible effect. And let me just show you. So if I send 0, if I raise 2 to the power of 0, I get 1. If I raise 2 to the power of -1, I get 0.5. And if I raise 2 to the power of 1, then I get 2. So you can see the effect that we're getting here. So 1 octave up results in 2, and 1 octave below results, in 0.5. The only thing that we have to fix is actually flip this around, because we want it the other way around, such that, like we had said prior, lowering the pitch increases the length of the ramp. So we want -1 to result in 2, and we want 1 to result in 0.5. So there's a few different ways that we can do this, but one might be to just multiply what we get from stash by -1. So we'll just flip that around. And now anytime we get, say, a higher value, let's actually just do it like this. A bunch of 12s, a bunch of -12s. 12 gives us 0.5, which is going to scale the length of our buffer by 0.5. Or take the length of our buffer, multiply it by 0.5, and then tell ramp to produce ramps of that length. And if we get a value of -12, it's going to do the opposite. It's going to double the length of the ramp. And the result is that we're going to play things back at different pitches, which is awesome. There's one other thing I want to show you. So if we wanted to use the R slider, I'm going to create an R slider, and I'm going to go into the inspector, and I'm going to put it into float mode, and I'm going to set its range to 1 so that these are the kinds of values that we get. And just patch those in here so that we're actually creating ramps that are of different lengths. What you'll hear is that as I change this, I actually change the pitch. And that's because we're still telling it, hey, over however many milliseconds, and, go from 0 to, in this case, 0.6. What we actually want to do is start from the length of the total file, but then actually scale that to the length of the sample that we're actually going to play. So what we'll do here is just subtract the end point from the middle. So we'll basically get the length of the region, the length of the file that we're playing. And then we will multiply that by the length. So now we're playing some sub-region of the sample, but we're playing it at the pitch that we want. And it doesn't matter how long that is, because we're adjusting the length of the ramp accordingly. So that's it for this time. Next time, we're going to talk about MC.MIDI player. I know that some of you really, really want this one. It's going to be a few weeks because I'm actually going on vacation. But I promise you that we will get to that one. That one's really cool because it actually allows you to kind of turn these signal style sequences into MIDI very easily with a single object and trigger VSTs living in Ableton or hardware that you might have or whatever, anything that uses MIDI, you can send with that method. So stay tuned for that one. In the meantime, get down in the comments and let me know what you're finding here. What's exciting to you? What is confusing? Anything that you want to learn more about. And of course, if you're liking these videos, please like, subscribe, notification bell, all that. You know the drill. It is helpful. All right. See you in 3 weeks. Make comments. I will respond to the comments before 3 weeks are up. And I'll see you next time. Thanks.